but we're dealing with molecules, not ions, and that's the difference. All right, let's look at oxidation and reduction organic. Now, if we define oxidation and reduction as definitions, there's actually two definitions of each. So for oxidation is an increase in the number of CZ bonds. And remember what Z equals, an electronegative atom, such as nitrogen, oxygen, halogen. Oops, halogen. The more of these bonds you have, if you increase the number of bonds to an electronegative atom for carbon, you've oxidized it in that reaction. And then reduction is the opposite. A reduction reaction is when you decrease the number of CZ bonds on a carbon going from reactant to product, okay? So that's one way to define oxidation. We'll look at the other definition in a second, okay? So for oxidation and reduction, here's some examples of some reactions. Now, I'm not giving reagents. We're just looking at different reactions we can do to produce new compounds. Now, all of these are single carbon compounds, and we're changing that carbon's bonding pattern to oxygen by doing oxidations as we go. So this is an example of methane. Now, methane has no bonds to electronegative atoms like oxygen. So it doesn't, we would say if I was looking at an oxidation number of carbon, even though it doesn't have a charge, I would say that's an oxidation number of 0, meaning it's not charged at all. That is a nice electron dense carbon. It's the most electron rich. It's the most reduced form of carbon. It doesn't have any oxidized bonds. If we take methane and we convert it to methanol, okay, now methanol has one CO bond. I might say that the oxidation state of this carbon right here was 1. It doesn't have a positive 1 charge, but in organic, it's bonded to a CZ bond once, so it has an oxidation state of 1. And so as I get higher in my oxidation state, I've done an oxidation. Now, rather than writing the word oxidation over and over again, okay, in this course, we're going to use the symbol. Some of you probably used the symbol for oxidation when you were in Gen Chem. Did anybody ever see an oxygen put in brackets before as the symbol for oxidation? I don't know if you have or not, but that is the symbol. So if we go from an oxidation state of 0 to 1, we have oxidized our carbon. And we can go on from here to go from an alcohol to, let's say, an aldehyde here. Now that carbon, that 1 carbon compound still has 4 bonds, is bonded to oxygen twice. Oops. So we have 2 CO bonds. And so this compound, I would say that carbon probably had an oxidation state of 2. Okay. So we've further oxidized. If you go from a ketone, how do you get to an oxidation state of 3? A lot of times in organic, for oxygens, the carboxylic acid is the functional group rather than the carbonyl. Carbonyls are usually oxidation state of 2. Carboxylic acids are usually a stable functional group of carbon for an oxidation state of 3 because they have a double bond to one oxygen and a single bond to the other. See that? So this has 3 CO bonds in it. 2 are sigma, 1's pi, right? That should say 3. That's messy. And then what is a stable structure for carbon that has an oxidation state of 4? The highest or most oxidized a carbon can be. Now, the reason the most oxidized a carbon can be is an oxidation state of 4 is because carbon gets 4 bonds. And so if all of those bonds are to electronegative atoms, and here's one example, carbon dioxide, then this is the most oxidized form of carbon, 4 CO bonds. All right. So if we are moving from less bonds to more bonds to electronegative atoms, we are oxidizing our carbon. If we move in reverse, obviously we're reducing the number of CZ bonds. We are reducing, doing a reduction. And the way that a reduction is symbolized is by putting a hydrogen in brackets. Now, why do we put a hydrogen in brackets for reduction? let's look at the second definition of reduction and oxidation, okay? So instead of defining oxidation and reduction as the number of CZ bonds, whether it increases or decreases, we can also take a carbon and we can look at the number of CH bonds a carbon has, all right? So if we increase the number of CH bonds, then we must be decreasing ZZ, then we are reducing, and vice versa. So we can also look at the number of hydrogens attached to our carbon atoms, and as they become more, we're the more reduced or saturated form of that carbon. So for example, down here, this is a good example of when we might use the second definition. Some of the functional group changes that we can see in a reaction don't include heteroatoms. So we aren't looking at nitrogen or oxygens or halogens being added onto a compound. Some of the reactions involve carbons changing their hybridization. For example, here we have an alkyne, okay? And here we have an alkene, and here we have an alkane. Now we're changing the carbon backbone up to different functional groups, but there's no Z atoms anywhere. So what we're going to do is we're going to look at how many carbons hydrogens are bonded to the carbons that are affected in this change. So I'm just going to use these dots to show there's 2 carbons here that are continually being reacted upon and changing, okay? And so from those 2 carbons, let's analyze. Here's an alkyne. The carbons that are changing to an alkene on this side, let's look at this carbon, for instance. Let's single one carbon out. This carbon has 0 CH bonds. Okay, it doesn't have any. But as we move to the next structure, that same carbon now has 1 CH bond. Okay, we're increasing the number of CH bonds. That's a reduction. So as we move to the right, we're reducing. That's why we put the hydrogen in brackets. Reduction is the increase in hydrogen bonds, if that makes sense. Oxidation is usually an increase in oxygen bonds, if that helps you remember. All right, and then as we move forward from an alkene to an alkane, if we were to do that reaction, it would also be a reduction. This carbon now has 2 CH bonds. So we're increasing its reduction structure. All right, so do you all see how that works? There's some examples in your book where you look at different reactions, and based on one compound changing to another compound, usually there's a functional group change, you can determine if it's an oxidation or reduction using either of those 2. All right, well, the title of our chapter is Oxidations and Reductions, so it only makes sense that we're going to discuss reductions first, right? I always think that's funny. But yeah, we're going to look at reduction reactions first. So if we're doing a reduction reaction, our starting material is being reduced to our products, and we're going to use reagents. The reagents that we use are called reducing agents. Reducing agents. So our reagents are reducing one compound to another by usually increasing the number of hydrogens, okay? So if we're increasing the number of hydrogens and we're looking at reducing agents, our starting materials, a lot of times our starting materials have hydrogen in them, H2. Now H2, I'm going to put that in parentheses because it's not always H2, but we're going to be reducing compounds by adding 2 hydrogens to a starting material. Now, how we add 2 hydrogens is going to be different. There's 3 different ways we can add 2 hydrogens or reduce a functional group, okay? There's 3 types of reductions. And they all add, not the molecule H2, but they all add quote unquote H2. Now, H2 is our simplest molecule that exists. It's hydrogen, right? Hydrogen is 2 hydrogen atoms bonded together by a single bond. So if I look at hydrogen real quick, this is how we draw hydrogen in organic chemistry and in Gen Chem, right? Hydrogen gets 1 bond, there's 2 electrons in between. Now, if I take hydrogen and somebody said, I want you to draw the subatomic particles of hydrogen, okay? There are only 4 subatomic particles in this molecule for hydrogen 1. The nucleus of this hydrogen atom contains one proton, right? Because it's H1, right? It's the number 1 on the periodic table. And then there's one electron outside of the nucleus. That is a hydrogen atom, H dot. So if you combine the two H dots, then we have 2 electrons connecting 2 protons. Subatomically, this is literally what hydrogen kind of looks like, right? I guess I wouldn't say literally, but this is our representation. Okay, it doesn't literally look like that, right? I can't see hydrogen. I can see this. All right, so if you think about hydrogen, we've got 2 protons and 2 electrons. If we're reducing a molecule using hydrogen type of reductions, adding hydrogen to a molecule, most of the time we are adding 2 protons and 2 electrons to the molecule. We're just going to do it in different ways. So the first way I'm going to show you, and this is kind of a summary of the reactions we'll be looking at, is the metal catalyst reduction. You're going to see some metal catalyst reductions where our reagents are going to be hydrogen and some metal catalysts. Our reagents are the hydrogen and some metal catalysts. Now, the metal catalysts can usually be palladium, expensive platinum, or nickel. Platinum is one of my favorite metals, and I was a organoplatinum chemist for quite a while. Have some publications on that, but platinum is expensive. So a lot of times nickel works for certain instances. Palladium is probably the cheapest catalyst for these reactions that actually works well. So you're going to see a lot of palladium chemistry going on in this book because it's a good compromise if you don't want to spend too much money. Still expensive though. All right, but these are our reagents that we're going to be using. It's a metal catalyst reduction, and our reagent is H2. So that's how we're going to add hydrogen in these molecules. We're going to literally add H2, okay? H2 is what will be added, 2 protons, 2 electrons to our molecule. So here's an example of that. These are going to be addition reactions where we're going to use these metal catalyst reductions. So for instance, if I start with an alkene has this pi bond in that double bond. That pi bond is weaker than all the sigma bonds. So what we're going to do is we're going to add hydrogen across that double bond. We've done addition reactions before. So we know that you break the pi bond and you add the 2 atoms across it. So we're literally going to add HH across the double bond. And we're going to use the metal catalyst to do that. Now, are metal catalysts consumed during reactions? What do you all think? Are metal catalysts consumed during a reaction? Do you use up a catalyst and at the end of the reaction it's gone? Let me see. I got to keep up with my chat. There we go. No, you do not consume them. When you add the quantities of reagents here, let's say that I add one equivalent, like 1 mole, and 1 mole of this, so 1 equivalent, you only add a small percent of metal catalyst in. You take the tip of your spatula, you put a little bit of solid on it, and you sprinkle a little bit of solid in. Actually, that's how I load my catalyst. It's kind of like making soup. It needs a dash of salt. That's how I kind of put a dash of my catalyst in. Most of the time, we do anywhere between 1% and 5% catalyst loading in a reaction. So let's say I know how much alkene I'm using. If I multiply that down and say I'm going to use 1% of this quantity, that's how much I put in. Sometimes the quantity is so small, if I'm running a small reaction, I can't measure it. That's why I literally just put a dash in. And you'll know that the reaction's starting when you put a catalyst in because you'll see the solution change. Ooh, and you'll be like, ooh, I've put enough catalyst in. So organic chemists, we get a knack for things. We've got a starting reaction. If we put our starting materials and reagents in only, those reagents in, nothing happens. Then we go grab our expensive little catalyst, and I just start sprinkling it in if I can't weigh it. Sometimes you can weigh it if the reaction's large enough, but if I can't weigh it, I sprinkle it in, and I sprinkle it. When I see the reaction start, I know I've added enough catalyst. Now that catalyst comes back out unconsumed. It just keeps reacting over and over again. But that's our metal catalyst reduction. We'll look at a few of those, okay? Now, the second way that we can add quote unquote hydrogen to our organic compounds to do a reduction is we can do a dissolving metal reduction. That sounds cool. And actually this uses, the book doesn't use my favorite second metal, but I've also was an organolithium chemist for some time and have publications on that as well in the literature. So lithium is my second favorite metal. Platinum is my first. But anyway, what we're going to do is we're going to take some metals and we're going to add, your book likes to use sodium, so you'll use that the most. So we'll use, our reagents are going to be sodium or lithium, because if you go to other books, you'll see lithium's actually the better one. It's just more reactive. Sodium or lithium metal. And we're going to use that inside a solution of liquid ammonia. Now, does anybody know about ammonia? At room temperature, what physical state is ammonia usually in? At room temperature, what physical state is ammonia usually in? Anybody know? Probably from Gen Chem. Not a liquid. It's a liquid here in this reaction. It's a gas. Sometimes they say when you mix your cleaning chemicals the wrong way, like if you're cleaning, you start mixing chemicals, you can get really sick. You can release ammonia gas, but it's very volatile. And it's a gas at room temperature and standard temperature and pressure. Now, in order to get liquid ammonia, we have to go down to cold temperatures. Now, your book doesn't emphasize this so much over the arrow. It just says, usually it says ammonia, but you can't literally run your reaction in gas because that won't dissolve anything. So you're going to run it in liquid ammonia. So you're going to do it at cold temperatures, like negative 78 degrees Celsius, okay? You can do a negative 78 degrees Celsius bath. If you take a little, dish, remember how we did the sand bath, like you put the sand in and we heated that stuff up, okay? Take that same glass dish. That's for hot reactions. If you want to do ice water baths, you put water in and some ice and you make a 0 degrees Celsius bath. You can cool your reactions down. How do you make liquid ammonia? Well, what you're going to do is you're going to keep the reaction, very cold in like a dewar. A dewar is a piece of glassware that's double walled, kind of like the, double walled containers we use that keep hot things hot and cold things cold. So we use a dewar to keep the liquid in. And what we do is we can either put liquid nitrogen in here. And now liquid nitrogen is my favorite to play with. You can see several videos on YouTube of people playing with liquid nitrogen. That occupied a lot of my spare time when I was in grad school. It's like, I'm really bored. I don't feel motivated. Let's go play with some liquid nitrogen. I have some extra. Because I did a lot of laser experiments. You've got to keep those experiments cold. A lot of laser stuff gets hot. So I'd go down and get the liquid ammonia, or liquid nitrogen. When my experiments were over, that's when I got to play with it. Throwing on carpet. I haven't tried that one yet, Alexander. Is that one cool? Super cool. I have done bananas. We've done balloons. Oh, it was really fun one day. My boss, I saw it online, but your dermatologist did it for me once. Very cool. We used to throw it across the floor and it would beat up. And we'd say, I'm going to clean the floor real quick. And we would just throw our extra out. Or sometimes we throw it up in the air and watch it. But one time we saw where people were blowing up balloons. And then they were putting them in a dewar that had the cold temperature. So above the head space, and of course this is just gas laws, we put the balloons in that cold head space above the liquid, and we got them collapsed down. And then we would throw them inside underneath my professor's door, which had about a 2-inch clearance. And so he was gone one day. He was out, I think he was in Japan, but he was coming back Monday. So on Friday, we blew up a whole bunch of balloons, cooled them all, shoved them under the door without breaking them. And then when he got in his office, he's like, how in the world did this happen? Tons of balloons. It was fun. I don't know. Okay. Well, anyway, another way you can make a cold bath is acetone. Now, acetone is a volatile liquid. It's literally a liquid at room temperature. It is 25 degrees Celsius at room temperature. But if you take acetone as your liquid and then you put dry ice chunks in it, which is solid carbon dioxide, inside of the acetone, the equilibrium between the acetone and the carbon dioxide will put you at negative 72 degrees Celsius. So that's how you can do a cold bath. But in that cold bath, you can add some liquid nitrogen from a container and keep it cold, and it won't evaporate as readily inside of a round bottom flask. Okay, now, what is that liquid ammonia serving as? That liquid ammonia is going to serve as your solvent, so that's great, but it has a dual role. It's also going to be your proton source. Because ammonia has NH bonds, those hydrogens are partial positive, so they're weak acids. So if you have a strong base, it will pull off that proton. Now, why is that important? The sodium and the lithium, and these are not the ions. Most of the time when we write sodium or lithium down, we always write the ion, like +1 charge. It's not a +1 charge here because it's the literal metal. You can't find this stuff like laying around because it's so reactive. Remember, these are in the alkali metal series from Gen Chem. You learned that. They are the most reactive of all of the metals on the periodic table because they only have one valence electron. And so because you have one valence electron, they are very apt to get rid of that. They're very electropositive anyway to be stable, to become stable. So these are electron sources. They are electron sources. So what's going to happen in this reaction is if you take, and I kind of covered it up now, I'm sorry. If you take 2 sodiums, and those are the metals that each have one valence electron, they will ionize to release 2 electrons into the media or into the reagent you're looking at. So they're going to be your electron source for reducing. And then the ammonia is your proton source, because once the ammonia is deprotonated or donates 2 protons to your starting material, you'll have some amides left over. That's an acid-base reaction. Okay, now, how are we adding hydrogen across a molecule then? How are we reducing a molecule? Well, we are going to add an electron to our molecule, and then what do we call this H plus? What do we call that thing? H plus? It's literally the nucleus of a hydrogen atom, right? H plus is a proton, right? So we're going to add an electron to our molecule, then we're going to add proton to it. We're going to protonate it. And then we're going to add another electron to our molecule, and then we're going to protonate it. And overall, look, oh, that's all the components of hydrogen. We're just going to add it piecemeal. Here's an electron from sodium for you. Here's a proton from the solvent. Here's another electron. Here's another proton. And overall, that adds up to quote-unquote H2. All right, the third type of reduction we're going to see is a hydride reduction. Now, have you ever seen this ending "ide" on an element before? Like chlorine's the element. What is chloride? Chloride is the what of chlorine? Gen Chem nomenclature 101, right? When you put "ide" on the end of an element, it's the anion, right? It's the anion. So we're going to use a hydride anion in order to reduce some compounds. Now, a lot of times this is followed by protonation, okay? So our reagents are either going to be sodium borohydride. I don't know if any of y'all have ever heard of sodium borohydride. When you were in Gen Chem and you had to do your complex polyatomic ionic structures, I bet you drew this thing. You had a sodium cation and you had your anion in brackets. I bet you've drawn it. It's a common one on worksheets. But we can either use sodium borohydride as a hydride source or lithium aluminum hydride. Ooh, you know, I like lithium. But really the sodium and the lithium are not our reducing agents. They are the counter ions. It's the hydride reagents that are going to be reducing. It's the borohydride. Notice it has 4 hydrogens instead of 3. Boron's in group 3 on the periodic table, and for that group, it gets 3 bonds. So when it has 4 bonds, it's what we call hypervalent. It has too many bonds. So it readily releases a hydride into solution or into another molecule as soon as it is in a reactive media. So when we put sodium borohydride in, it releases a hydride to become its regular valency, a BH3, a borane. Now, lithium aluminum hydride is the same way. Now, if we think of aluminum forming coordination compounds with hydrogen, okay, or bonds, as you might call them, with ligands, then aluminum is in group 3 as well. It should only get 3 bonds, okay, or have 3 anions around it, however you want to think about that. But instead it has 4. So instead of neutral, the aluminum is negative. So once again, hypervalent. And so it will release a hydride into solution or into another molecule when it's in that reactive media. So these are hydride sources. Now, if you have a metal hydrogen bond like these do, the hydrogen is more electronegative than the metal, okay? Because remember, it has carbon's electronegativity, which is to the right of the metals. So the hydrides will release. You're basically or effectively releasing H- into the media. And so that's your hydride source. Now, a lot of times, after the hydride source is added, you'll then be adding a proton back to solution. Or protonating the solution if there's an anion available. So really what the hydride adds, a hydride is the nucleus of a hydrogen atom plus 2 electrons. And then we're also going to add a proton. So overall, if you add up the protons and electrons, we're adding H-, H+, to a molecule, and that's how we're going to add hydrogen. So there's 3 ways to quote unquote reduce the compound with hydrogen. Okay, catalytic metal catalyst reductions with hydrogen gas and a metal palladium catalyst usually, dissolving metal reductions with sodium or lithium and liquid ammonia as our proton source, and hydride reductions where we use hydride releasing agents, sodium borohydride or lithium aluminum hydride, and sometimes followed by protonation. All right, do you see that there's different ways we can reduce the compound? These are the reagents. These are the reagents that will reduce, and this is how they do it. So let's go into our reactions. So in this chapter, we're going to be focusing on reduction reactions, the common ones in organic, and then oxidation reactions that are common, okay? So here's our first reaction. It's the catalytic hydrogenation of an alkene. Now this is the H2 with palladium catalysts one, that first one on the list. So what can get reduced? Alkenes can get reduced. They have pi bonds, so we can add hydrogen across the pi bond. So if we start with an alkene and we add our hydrogen gas with our palladium catalyst, we could also use platinum, we could also use nickel, but palladium on carbon, it's a special type of palladium that's activated, and it's cheaper than regular pure palladium because it's mixed with carbon. So that catalyst works best. So it's the cheapest. So your book's going to use that most often. That's the catalyst you're going to see. And what we're going to do is we're going to add HH across that pi bond. So we're going to reduce it down to an alkane. So by adding HH across that pi bond, we form the alkane. Now I'm going to redraw this because, you know, I like to tuck my hydrogens in. Literally in a reduction, you go from double bond to single bond, okay? Now, when the hydrogens add across the alkene, they're going to add syn. Do y'all remember what syn means from the last exam? They add to the, what does syn mean? What does syn mean? All right, so here's an example reaction. Here we're going to take a cycloalkene. This is the 1,2-dimethyl cyclohexene. And we're going to add our reducing reagents to it. So we're adding hydrogen with palladium on carbon. And so when I initially reduced this, if I was doing kind of 2-dimension, you might think, okay, there's my product because I took the double bond out. But because there's a syn addition, it's adding to the same side. If I added the hydrogens from the bottom, my methyl groups go up because they're adding to the same face, the bottom face of that ring. Now I've got 2 chiral carbons that I formed here. So instead of both hydrogens adding to the bottom, we could also add both hydrogens to the top here, which would push our methyl groups down. But as we see, with 2 chiral carbons, if we draw the structure 3-dimensionally to show that syn addition, this is a meso compound. It's got an internal plane of symmetry, which means that its mirror image, enantiomer, is the same compound. That's not an enantiomer, that's the same compound. So when I go to draw this product, yeah, I am forming 2 chiral carbons. When the hydrogens add syn, they're adding to the same face. So it doesn't matter if I've had the hydrogens going down or up, we're going to form the cis meso compound here. The mirror image is the same as itself. The hydrogens add top or bottom, you'll get the same result. Okay? Now here's an example of how the mechanism is running. Okay? Now notice I'm putting mechanism in quotes. I'm trying to give you an idea of why it's syn. So if you start with the palladium catalyst, the catalyst we know has empty d orbitals. You know, it's a transition metal. It has partially filled d orbitals with electrons, as well as other electrons inside the catalyst. But it has several electrons. It also has empty orbitals. So when we add the hydrogen gas, start bubbling that in, our catalyst bed, the surface of the catalyst, coordinates those hydrogens, and they add, it's called an oxidative addition, to the palladium catalyst. So when they add to the catalyst becomes oxidized. Okay, you don't need to know that, but I'm just kind of showing you what's happening here. Okay, now there are still d orbitals that are open on this catalyst where electrons can coordinate. Well, the alkene comes in, and we know that alkenes are flat, so I'm going to draw this thing flat. See how I've drawn it kind of planar? The reason I'm drawing it planar to the face of the catalyst bed, if you think about it, there's p orbitals. Like that pi bond there is a p orbital above and below the molecule, where that's where the pi electrons are found. Those are the electrons that are going to be able to coordinate to the catalyst. They're going to sit inside of some empty d orbitals and coordinate. So when the alkene approaches the catalyst, which has had hydrogen oxidatively added to it, there's going to be a hydrogen exchange. And this is not exactly how the mechanism goes. I wouldn't teach this in an organometallics class. But basically, we're going to move the electrons around. The pi bond is going to accept this hydrogen. We're going to give the catalyst its electrons back that we took to embed hydrogen. And then we're going to release that hydrogen here. But it's from the same face. So as soon as the pi bond is being converted to a sigma bond to make that CH bond, it no longer coordinates to the metal catalyst bed. Okay, it's got its electrons back. This is called a reductive elimination, but now the hydrogen's left and it's added to the same face, syn, of the alkene. So that's how we get our syn addition. And we go down to the alkane. Because the alkane only has sigma bonds, it doesn't have any other electrons that can coordinate to the d orbitals of our metal, okay? Like a square planar d orbital. So it releases and our product just floats away. And now the catalyst is back to its normal state. It can add hydrogen again, do another process. So it's a catalytic cycle. It keeps going and the alkene comes in, the alkane goes out of that cycle. So that's how the catalyst keeps being reused. And that's how we get our syn addition of hydrogen. All right. That is known as a catalytic hydrogenation. And we've probably heard of this term hydrogenation before. If you looked at the very front of this, what is it called? PowerPoint or whatever you want to call it. At the beginning of the lecture slides, you notice I had a picture of some natural oils on there. Has anybody heard of partially hydrogenated oils before? Partially hydrogenated oils, right? Are they good for you? I've been told they aren't, but where do we find those? What's a food that has that you would buy frequently as partially hydrogenated? Anybody know? It's not butter. I can't believe it's not butter. What about margarine, right? Margarine? Yes. And don't ask me how the whole process works. I'm not a food chemist, but I do know about hydrogenation. If you take an alkene, which we've talked about these fatty acids, right, in the past, oils and fats with the fatty acids. And we said a lot of them have double bonds, like cis or trans double bonds, cis being better than trans, right? And so a lot of your oils have cis bonds. A lot of your fats, which are solids at room temperature, have the trans double bonds or are fully saturated as the alkanes. Do y'all remember that? So if we take an alkene and we've got cis alkenes, trans alkenes, whatever, and we hydrogenate it, we add in hydrogen with our catalyst, we are going to go down to the alkane. Well, that reduction process, that reaction is an exothermic process. It releases heat. Exothermic. And so the amount of heat released is called the heat of hydrogenation. Makes sense, right? It's the heat released from hydrogenation, okay? And it turns out that chemists can use hydrogenation to figure out stabilities of alkenes. Do you remember we learned alkene stability trends? Like we learned that the more substituted an alkene is, the more stable it is. But we said for the di-substituted alkenes, we had 3 different types. We had geminal, which don't have stereoisomers, and then we had the 2 stereoisomers, cis and trans. Do you remember those were the 3 different types of alkenes? It turns out that trans alkenes are more stable than cis alkenes, which are less stable. Now, how do we know this? We can use theory like dipole moments, and we can talk about how the trans isomer has a smaller dipole moment. Because of that, it's probably a more stable compound because it's less charged. What we like to call that hand waving in chemistry, because we're taking theory and we're trying to match theory with what's known. Okay, like I postulate this, but how do we prove it? Theorizing based on book knowledge is great, and that's great hand waving. But we've got to be able to prove something in order to call it, fact. How do I know that trans isomers are more stable than cis? Well, if I set up an experiment where I hydrogenate 2 alkenes that they're stereoisomers of one another, one's the cis version and one's the trans version, but when I reduce them down to the alkane, they give the same alkane out, I can use their heats of hydrogenation to tell which one was more or less stable. Now, remember why I can do this, okay? So if I have an energy diagram, since we're talking about thermodynamics here, okay? If I have a starting material and I do a heat of hydrogenation, we're saying that's exothermic, my product's going to be lower in energy here, okay? So remember that this downhill energy from starting material to product, think about delta H, that's why our delta H is negative there. That's the heat of hydrogenation. And the larger this arrow, the larger the heat of hydrogenation, okay? Now, if we look at 2 reactions, let me color code them for us. If we take the cis isomer and we hydrogenate it with hydrogen palladium catalyst of cis-2-butene, and we hydrogenate it down to butane, that is exothermic by 120 kilojoules per mole, okay? That's its heat of hydrogenation. If we do the same reaction with the trans isomer, trans to butene, and we reduce it using the same conditions down to butane, notice we have a similar alkane product, okay? So our product's the same, it has the same energy. Now notice the heat of hydrogenation for the trans alkene is negative 115 kilojoules per mole. We can go back and we can use this knowledge to set up an energy diagram to figure out which starting material is at higher and lower energy. And we're going to work backwards because the product is always the same. The product was butane. Okay, so we know butane is the product of both. It's always at the same energy. Now, if our trans isomer had 115 kilojoules per mole, okay, negative 115, let's just draw kind of an arrow. Okay, well, let me just put it in blue. I'm not going to put all that. Delta H. Here's my delta H for my trans isomer. So going from product, the starting material is at this energy, 115 kilojoules per mole, higher in energy. So this is my trans isomer. Okay. Now, if we look at the cis alkene, notice that it's exothermic by 120 kcals per mole. So it's going to go up a little bit more. And this is not to scale. I warn you, it is not to scale. So from the product to the starting material now, right? The starting material is going to be higher. All right. So now with the starting material higher for the cis, if we look at our two starting materials, the one that's higher in energy is less stable. That's the cis. The one that's lower in energy is more stable. So what we've done is we've used heat of hydrogenations to figure out the stability pattern of alkenes. It's kind of brilliant. Now, I wish I would say we. Let me strike that. I didn't do this. Another chemist did this. And it's so simple. Sometimes the best experiments just come straight from knowledge of theory, okay? Combining a problem with a theoretical way to solve it. And it all comes down to the basics. So I think that's a really beautiful experiment. But it shows us that heats of hydrogenations can determine alkene stability. Pretty cool. Poetic. All right, now, what about the other alkenes? If we think about hydrogenations of other alkenes, now they don't, if you are mono versus di, tri, and tetra substituted, you're not going to form the same alkane product when you get reduced, because you're going to have different substitution patterns on those carbons that are reduced. So what about our mono versus di, tri, and tetra substituted? It turns out that when we run a hydrogenation with a mono substituted alkene, that's the most reactive. Like it reacts the fastest with that catalyst and gets reduced the fastest. And it turns out the least reactive is this tetra substituted. It reacts the slowest. Now, why is that? Okay. If you think about the mechanism, okay, I'm going to go back to the mechanism. Once the hydrogen is added to the catalyst bed, the surface of the catalyst, remember that the alkene has to come in close enough to coordinate with the catalyst. They both coordinate with the catalyst in order to do that hydrogen electron exchange, okay, to form product. If you have a really bulky alkene, it's tetra substituted, that pi bonds, remember the pi bonds are only so long, it's going to have a harder time getting close to the catalyst bed to coordinate and do the chemistry. You're going to have to move those R groups out of the way with a little bit of strain, right? And that takes time through electrostatic repulsion. So it turns out then that the more crowded you are, more substituted, the harder it is for you to complex to the catalyst surface. And the less substituted you are, there's less sterics involved in your complexation. So the reaction on that catalyst bed is faster. Does that make sense, guys? Now, this is kind of interesting, right? Because if you take, let's say that you take an oil, okay? Let's put this to practice now. I'm going to delete this. Okay, so I can just do an example of why do I need to know this. All right, let's say that we are taking a fatty acid. It's an acid and it's fat. Okay, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, I'm just making up fats here. Okay, you don't even have to draw this. This is just an example. But here I'm going to have a cis alkene. Oh my gosh, I accidentally made an omega-6,9 fatty acid. That's brilliant. I didn't even mean that, guys. All right, let's say that I take this fatty acid and I add in hydrogen gas with palladium on carbon catalyst, okay? Now, I have two alkenes. I have a cis alkene and I have a trans alkene. Okay. Now, if I have a cis and trans alkene, they can both be reduced by hydrogen with palladium on carbon. So if I add in two equivalents of hydrogen, meaning twice as much to be able to reduce two alkenes, I'm going to go all the way. I'm going to just call that a polar head. I'm going to go all the way to the alkane. I'm not even going to count my carbons. But both of these alkenes are going to be reduced. Okay? And that's because alkenes react with hydrogen on palladium to go down to the alkanes. So we'll have a saturated fat. Okay? Now, so we would have said we fully hydrogenated that oil. You see where I'm going with this? We fully hydrogenated that oil. Now, let's say instead that I only use one equivalent of hydrogen. If I use one equivalent of hydrogen, I've got my cis alkene and my trans, I don't know why I'm writing alkene, and my trans alkene. Which one's less stable, aka more reactive? Who's less stable and more reactive? Who's going to reduce? The cis. You are right. The cis is going to react faster because it's less stable. It's more exothermic. So the less stable alkene will be more reactive. Words we've learned this semester how to determine things. They're reverse sides of the same coin. So more reactive. I know that doesn't look like more reactive. That's why I'm saying it. But what would you call this reaction? It's not a full hydrogenation of this oil. What would you call it? I'm only going to reduce I think I have too many carbons there, but I'm only going to reduce, right? The cis alkene, we've hydrogenated it. Wouldn't you call that a partially hydrogenated oil? I think that's what, yeah, partially hydrogenated. Good job, Danielle. So that, if you think about that, that's kind of what's happening here, okay? You take an oil, you add in less than the full equivalents, it turns out, and remember, cis fats are the ones that make it more liquidy. Because they form kinks in your fats. We learned that before. So you take out all the cis and you get that nice straight zigzag of the saturation there, plus the trans saturated, you're becoming more solid. All right, so that's how that works. All right, let's move on. So we've learned about hydrogenation reactions of alkenes. It turns out we can use the same reaction conditions, hydrogen on palladium, to reduce aldehydes and ketones. Aldehydes and ketones have reactive carbonyls, but we can add HH across their pi bond as well, just like an alkene. So this is going to be a simple extension here. If I take an aldehyde, that's a carbonyl at the end of the chain, and I add hydrogen with palladium catalyst, I'm going to add HH across that pi bond. So I add HH across that pi bond. And so that will bring me down. If I look at this, there's only one carbon attached to that aldehyde carbon. That's a primary alcohol. So another way we can make alcohols, we've learned a lot of ways of this term from alkyl halides and stuff, but and alkenes, is we can take an aldehyde and we can reduce it to a primary alcohol. I'm going to clean that up. Oops, I ran out of room. There it is, 1-pentanol, just drawn more in zigzag mode and tucked my hydrogens in. All right, we can do the same thing with ketones too. You've got a ketone. We're going to hydrogenate it. Remember, it's a syn as well, same type of reaction. So if we add HH across that pi bond, okay, I'm going to redraw this and tuck my hydrogen bonds in. There we go. We've made a secondary alcohol. That carbon there that was ketone, it's because it has two carbons attached to it. So a ketone becomes a secondary alcohol. There you go. So we can do that hydrogenation with alkenes as well as aldehydes and ketones. Pretty cool. Same type of mechanism. All right, now what about alkynes? Alkynes have triple bonds, right? Instead of double bonds, they have pi bonds. It turns out they can be fully hydrogenated as well, okay? So if I take an alkyne and I add hydrogen with palladium on carbon, it turns out it will go down to the alkene first. So we will add HH across one of the pi bonds. Remember, there's 2 pi bonds here. 2 pi bonds in an alkyne. And so we can get the cis alkene first, where we get the syn addition of 1 pi bond if we add 1 equivalent in. But that cannot be isolated, and I'll explain why in a little bit. It keeps reacting. That's why it's in brackets. A second equivalent of hydrogen will add to the molecule in order to produce product. So we're going to add another equivalent of hydrogen. So we'll have 2 total, H2H2, across our alkyne to give us an alkane. So we'll go all the way down to the alkane. We'll fully hydrogenate those double bonds, or pi bonds, I'm sorry. Now, why can't we stop at the alkene? We can't stop at the alkene because, oops, I'm going to go back a few slides, okay? Once the alkene is, if we had an alkyne, so here we've got a triple bond. Let's make that a single bond. I'm not going to try to draw the whole thing again, but imagine this is an alkyne. I'll use a different color. Okay, there's our alkyne. When the alkyne reacts and produces 1 hydrogenation, we still have an alkene after the hydrogens have been added. Remember that alkene has pi bonds. And so the pi bonds coordinate to the metal. So they haven't uncoordinated from the metal yet. So we can't get the alkene off the catalyst. It's a ligand, it's coordinated. So even though hydrogens have been added, it hasn't been released yet. The only way to release that from the palladium on carbon is to break all the way down to the alkane. Now it has no more pi bonds. It can't coordinate to my metal. It's released. It can go back into solution and it's released as a product. So that's why we can't isolate alkynes down to alkanes. The catalyst will not let go of that pi bond. All right. So we go all the way to the alkane. So in general, when we run this reaction, oops, the reagents are usually understood to be in excess. So if I show this reaction again, I'm going to use hydrogen with palladium on carbon. It's understood that this hydrogen's in excess. That means at least 2 equivalents. Because when we put an alkyne in with hydrogen and palladium, we're going to use at least 2 equivalents. We have to go all the way down to the alkane to get product out. So for example, if I have this compound here, this is 2-butene. There's 1, 2, 3, 4 carbons here, 2-butene. When I hydrogenate that, it's going to fully hydrogenate to the 4-carbon alkane. Alkyne goes to alkane. There we go. So I've added 2 equivalents. When we write reagents over the arrow, a lot of time that means that the reagents are added in excess. So sometimes we write that we've added 2 equivalents or excess, and sometimes it's just understood. So we just have to know the stoichiometry of the reaction. We have to understand alkynes fully react with 2 equivalents to make the alkane. All right. Can we stop at the alkene? That's a general question I get, like in class, someone will raise a hand, but can we stop at the alkene instead? Is there any way to do that? Yes. If we used, instead of palladium on carbon catalyst, if we ran the same reaction of an alkyne with hydrogen gas, but instead used something called Lindlar catalyst. Now, Lindlar catalyst is what you'll always see in the class with the arrow. We call it a poison palladium catalyst. And poison just means that it's a less reactive palladium catalyst. It is, if you ever want to know, you'll never see this again after this slide, but if you want to know what Lindlar's catalyst is, there's your ingredients there. All right. When I go into the lab and I run this reduction of an alkyne to an alkene using Lindlar catalyst, the bottle literally says Lindlar catalyst on it. So I actually had to look up these ingredients at one point in my life. Now they're in the textbook because I think people kept asking. So we're like, you should put in what Lindlar's catalyst is. But this is how you'll see it over the arrow. But what we're going to do is we're going to do that syn addition. So we'll stop at the cis alkene. So this is only going to add one equivalent of hydrogen. We're going to have to understand that because the stoichiometry, we don't give stoichiometry in our reactions that we write, okay? So if I take one equivalent of an alkyne and I add hydrogen in Lindlar catalyst, I go down to the cis alkene because my hydrogens are added syn. Syn. I can't write today. All right, so we can make a cis alkene using the poison palladium catalyst, Lindlar catalyst. So for example, we looked at butane a second ago. We said if we take butane and add hydrogen on palladium catalyst, we make the alkane. If we take butane to butane and we add hydrogen with Lindlar catalyst, we don't make butane, we make cis to butene. Cis to butene. All right, so we've got a second way. We can add one equivalent. All right, can we make the trans alkene? Yes, we can. In order to make the trans alkene, we're going to use that final method we talked about of reduction called the dissolving metal reduction. All right, remember that? It's got the sodium or lithium with the liquid ammonia at cold temperatures. Your book leaves out all that information. That's all more in reaction setup. But if you use sodium or lithium, your book likes sodium more. It's not as dangerous. I like to live on the dangerous side. A little fire in here and there never scared me. Just joking. Not really. But the general reaction here is that if we take an alkyne and we react with sodium or lithium, my favorite, in liquid ammonia, we are going to get down to the trans alkene. So the hydrogens on either side, I don't know why I'm drawing this in green, I apologize. All right, the hydrogens on either side are going to add anti to one another, okay? So this is how we get the trans alkenes out from an internal alkyne. All right, so for example, we've got that 2-butane again, and I use a different color here, I'll use black. Okay, if we have 2-butane and we hydrogenate or reduce with sodium and liquid ammonia, that 2-butane will go down to the trans 2-butene. Stereospecific, we're going to get that product. And the mechanism is interesting. So I'm actually going to go through the mechanism of this one because it helps you remember the reagents a little bit. And it helps you remember that why it's trans. So if I take an alkyne, yeah, let's do it in black so I can actually read it. Okay, if I start with an alkyne, okay, and I put in my metal. Now I'm going to put in sodium and I'm going to show the electron because remember, mechanisms show the movement of electrons to go from reactant to intermediates to products using curved arrows. So I'm going to use curved arrows. Do you all remember there's two types of curved arrows? There's the double-headed curved arrow, and then there's like kind of the fish hook arrow. Do y'all remember that? We've briefly been over it this term when we were doing homolytic versus heterolytic bond cleavages. Yes, so you do remember. Good. And yeah, so if you have a double-headed arrow, that was showing the whole bond gets moved, right? If you think about that, though, really the whole bond, when we were moving those, was 2 electrons. You're moving 2 electrons, a pair. When we homolytically cleaved, it was half the bond. What that represented, that single fish hook, was that you were moving 1 electron. Do y'all remember that? So the double-headed is 2 electrons moving as a pair. A single-headed is 1 electron moving. Well, that is going to be what we're going to watch our hooks in this mechanism because sodium only has one electron in its valence shell. We would call that a radical. It's a radical. It's an unpaired electron, okay? But what we're going to do is sodium is what we call a hot metal. Lithium is the hottest. It's like, are you hot or not? Okay. Do y'all remember those websites? Those were cruel. But you're probably too young. Sodium is a single electron. It's what we call a hot metal in polymer chemistry. It's going to give up an electron really easily. So where's that electron going to go? Well, you see how there's a lot of space around the alkyne, like open, empty space around that atom? Because it's sp hybridized, that's called an anti-bonding orbital. Anti-bonding orbitals mean empty space. So if my pi electrons are on the inside, those are called the pi bonding orbitals, right? Then the anti-bonding orbitals are the empty space on the outside where there's nothing going on. There's no electron density found. So sodium is going to dump its electron in one of these. So if this is a pi bond, for pi bonding, this is the anti-bonding empty space, okay? Sodium's going to dump one of its electrons in the empty space around carbon. So it says, here you go. It's like hot potato. You take this. I don't want any more. Okay, now carbon can only get 8 electrons. So as soon as sodium throws an extra electron at carbon, it's got to break a bond. So it's going to move both electrons over to the other carbon. Now notice how I did this, okay? I didn't use the arrow like this. On the bottom, I moved the 2 electrons over to keep carbon from having more than 8 electrons. I moved those 2 electrons over on top. The reason is electrons repel each other. As soon as this electron gets put here, the other carbon electrons are like, ew. And electrons, right, they repel each other. So the pair of electrons that moves away because of the repulsion is going to move as far away in space as possible, which is going to be right here. And this is going to set up that trans or anti stereochemistry. All right, so if I draw the product of the step, this basically tells you everything you need to know just right here. So now we have a double bond because we broke one. And we've got in an orbital here, I'll just draw it so you can see it. We've got a single electron. Now, single electron's called a radical. They're not extremely stable. But over here, we've got an orbital. And it's got 2 electrons in it. This is a carbanion. It's got a negative charge. Okay. And then the sodium cation's like, oh, okay, I'm happy now. I'm stable. I'm a sodium cation. All right. At this point, we've got a carbanion. That's a strong base. So this thing's floating around in liquid ammonia, which is like NH3. I'm going to draw that as H and H2 so I can deprotonate with it. Here we have a strong base. This is a weak acid, right? That strong base is going to deprotonate. So the anion here picks off the solvent's proton, weak acid, and we're going to protonate that. So notice we've added an electron in the first step, just as I promised earlier, and now we've added a proton. See that? Electron, proton. And so now our product here of this step, which is an intermediate, looks like this. So we've added 1 proton, 1 hydrogen on. Now, radicals are not stable. This is where the 2 equivalents, and I need to kind of point that out here in my reaction details. When we put sodium and liquid ammonia over, we understand that it's 2 equivalents of sodium that's reacting because we need 2 electrons and 2 protons, okay? So usually over the arrow means you have enough, you have excess anyway. It's not usually the limiting reagent. Usually the starting material is the limiting reagent. But anyway, we're going to have a second equivalent of sodium come in, all right? Or it's already there. It says, hey, I'm going to dump my other electron in the space too, but because now that carbon's electron deficient, it needs a full octet, so it'll take it. And so this will get us down to another carbanion. Okay. And then that will subsequently be protonated as well. Oops, I didn't draw that good. H2NH. I'll show that NH bond. So now the anion is going to be protonated again by the solution. All right. And so we've added another electron, another proton. We've effectively added H2 trans due to electron repulsion across that double bond. RH on one side, HR on the other side. Remember, HR is always watching out for the people that pay them, not you. I don't know. Okay, anyway, let's see here. So we've added HH trans across the double bond. Now, I did forget a byproduct here. I'm bad about that. Whenever we deprotonated, we've got an amide floating around in solution each time we deprotonate. That's the anion of that ammonia, amide. All right, but that's the mechanism. Can you see now the storyline of how the reagents work? I feel like once you see the mechanism, it helps you understand what the reagents are doing so you can remember them better, and it helps you remember why they create the trans geometry. Very nice. Okay, so let's kind of put this together now, because we had our alkenes, and we know alkenes and carbonyls both react with hydrogen and palladium on carbon to either produce alkanes, or alcohols, okay, depending on what reaction we're looking at. So those were our first two reactions, the hydrogenation of an alkene, the hydrogenation of a carbonyl. They had HH across the double bonds there. But then we got into alkynes, and we learned that alkynes can be hydrogenated three different ways, or I'm sorry, reduced three different ways. They can either be reduced fully with two equivalents of hydrogen on palladium, okay, all the way down to the alkane, that palladium carbon catalyst. Or we can add one equivalent of hydrogen and use that poison catalyst, the Lindlar's catalyst, and that will get us down to the cis alkene if we have an internal alkyne. And then if we do the sodium or the metal reduction, the dissolving metal reduction, then we can take the alkyne down to the trans alkene. So this is very versatile. We have three different ways to reduce, add hydrogen across pi bonds for an alkyne. And if we have stereoisomers that we can form for an internal alkyne, we can make the alkane, the cis, or the trans alkene. All right, pretty cool, right? We have one more reduction sequence to get through. We'll take a break after reductions, okay? The other type of reduction that we said we were going to do on our first page, so we had the catalytic hydrogenations, we had the liquid dissolving metal reductions. We've done both of those. It was the hydride reductions. Do you remember the hydride reductions, H-? The reagents that you could use to do a hydride reduction is lithium aluminum hydride. You could also use sodium borohydride. Okay, now our book likes lithium aluminum hydride. It's the more reactive of the two. So whether you have lithium aluminum hydride or sodium borohydride, lithium aluminum hydride is the more reactive version. And it's because the aluminum hydride bond is more polar. And because the aluminum hydride bond is more polar, the hydride's more partial negative. So it is released more easily into the solution. And that's the hydride is going to be more reactive. So this is our more reactive substance that we'll mainly do the reactions with. Now, remember, lithium aluminum hydride is your hydride source. That's kind of what we see when we see the lithium aluminum hydride. We say, okay, it's going to literally release a hydride anion into the solution, okay? So we have two general reactions that we can do with lithium aluminum hydride. And what we're going to see the hydride is a good nucleophile. Have you heard of good nucleophiles before? On the last test, I think that your mind was probably spinning with nucleophiles, right? For substitution reactions, right? What type of substitution reactions do good nucleophiles do? SN1 or SN2? What do you all think? I had to take a swig of coffee there. Good nucleophiles, strong anion nucleophiles. Are they going to be SN1 or SN2? Do y'all remember? Or was it all a blur? Tehran knows, yep, SN2, very nice. So what we're going to do is we're going to look at reactions we've seen before, and we're just giving you a new nucleophile. These hydride reagents are going to do SN2 reactions. Very nice, very nice. So when did we do SN2 reactions? We did a lot of them. But in the SN2 chapter, there were two instances. Well, there was the alkyl halides. So do you remember if you have like a primary or secondary, a methyl primary or secondary alkyl halide? Those are the ones that do SN2s. So what we're going to do is we're going to add our hydride to the alkyl halide, and we're going to substitute the halogen for our nucleophile. And it turns out when we do that, we're going to make the alkane, because we're turning it back into a hydrocarbon chain. So notice the reagents, though, in this reaction. So if you see this reaction set up, we're going to add lithium aluminum hydride first. Once the hydride's formed, we're going to pour in water. Okay, now here's why. Lithium aluminum hydride, the aluminum hydride has 4 hydrides that can be released on it, which means sometimes there's excess nucleophile in the solution. That hydride can also be a strong base. So whenever we stop a reaction that has lots of strong acid or strong base in it, we do something called working up the reaction. And so this is called the workup. After the reaction's complete, we've done the SN2, there's going to be some extra hydride, lithium aluminum hydride laying around. So in byproducts. So what we do is we add in water to neutralize the solution. Remember, water's amphiphilic, it can be an acid or a base. So if we got extra hydride laying around, we can protonate it, okay, with our water, which releases hydrogen gas. Now, hydrogen gas, boom, can be explosive. It turns out when you work up this reaction, when you're adding water to excess hydride agents, especially lithium aluminum hydride, which is really reactive, you can release hydrogen gas very quickly, and the reaction's exothermic. So if you were to just take your reaction and then in step 2, after the reaction is complete, dump in water really quickly, you can actually cause a fire. And many a great chemist have caused lab fires, because the reaction's exothermic. It's usually done in organic solvents. Organic solvents, a lot of them are hydrocarbons or ethers, and they are extremely flammable. So you put hydrogen gas in, that's being released, exothermic and flammable solvent, you have basically a recipe for fire and fuego. So you have to be careful. So if you're ever doing a lab situation with this, one great word of advice that for some reason, if you ever did this reaction, you would remember your professor saying it right before you dumped the water in. Add the water slowly. We always want to work up reactions where we have to neutralize slowly. Like you wouldn't throw water into a strong acid or a strong base, right? That's scary stuff. We learned in the safety lab that you always add acid to water, right? Always add acid to water. You never add water to acid. And if you do it, you have to do it slowly, because it's so exothermic and dangerous. All right, just a little word of advice to you. But that's our alkyl halide. Let's look down at the mechanism. And I think you could probably figure this mechanism out because it's an SN2. So for our SN2 mechanism, our aluminum hydride reagent releases the hydride, and that hydride does a backside attack on our alkyl halide and kicks it out in one step. So this is an SN2 reaction. And that's how we make our lithium halide salt. That stuff gets everywhere in lithium chemistry. And then our aluminum hydride. All right, as a byproduct. Okay, let's look at the second reaction we can do with this. Our second reaction is it's an SN2 with an epoxide. Now, we're using a good nucleophile. And so if we have an unsymmetric epoxide, I'm going to set this up. Let's put 2 hydrogens on this side of the epoxide. And let's put 2 R groups on this side. This is an unsymmetric epoxide. And if you have an unsymmetric epoxide, remember when you have a hydride reagent, that's a good nucleophile. We're calling this a base-promoted ring opening reaction. Remember that the hydride is going to add to the less substituted carbon because this is an SN2. And an SN2 always attacks the least substituted carbon. So when our hydrogen adds, so when we release the hydride, oops, sorry guys. My screen hates it when I drag my pen. It's hard to do mechanisms. Can you tell? Okay, let's see. It's not letting me drag my pen, but you get the point. The hydride attacks it, and that's going to open our epoxide up, and we will get our alcohol out. So if we had an unsymmetric epoxide, we always, because it's SN2, we're going to attack the least substituted, okay? So here's that mechanism down here a little bit better. Here we have an unsymmetric epoxide. We've got our aluminum hydride, okay? That hydride is going to attack the least substituted carbon, and it's going to open the epoxide up, our base catalyzed or promoted ring opening. All right, once we add that hydrogen on, we have an oxy anion on the other side. Is it open? This is where the water comes in. So step 2, we've opened up the ring. Now we're going to add the water in. So now, and I'm going to redraw this actually, HOH, because I'm going to use the water as a proton source. So we're just going to protonate that oxy anion. And now we have the alcohol. And I guess you could put hydroxide as a byproduct there. All right, but that's how we get the alcohol.